Lydia, am I allowed to take off my mask or? But should I put the screen back or better not? Yeah, I mean, it's fine. Okay, hi everyone. Welcome to the second tutorial for the course of Advanced Topics in Quantum Information Theory. And so today the topics of the tutorial will be the following. So first, I'll just repeat in more formal manner the answer to the partial trace question that Ralph received in a lecture, and show you how in the matrix form we can take the partial trace if we have two qubit systems. I think it's on. Okay. Then again, the repetition of the lecture will be, we'll look again at the swap, for the qubit swap, and then the pooling procedure, both for real qubit and the virtual one. And finally, we will again see how we can compose virtual qubits. So most of these points will be in some manner repeating what already was in the lecture, but I can go a bit slower, and you can also ask questions if particular steps are not completely clear to you. Okay, so let us start with the partial trace. So suppose that we have two systems, A and B. So the states which describe the joint state on these two systems, they live in this joint Hilbert space. And suppose that we have the density matrix which describes such a joint state between two systems. And if we say that for the system A, we have the basis IA, and for the system B, we have the basis IB, then in a general case, we can always write the joint density matrix in terms of brackets as the following. So it will be the sum over ij kl, cij kl, ij the first system, A tensor product the kl on the second system, which is B. And this corresponds to the density matrix. So in general case, we would have, so here we have the rows, right? And we have the columns. And basically, yeah, so here, it's 4x4 matrix. So here I'll look at the case where the dimensions of these two systems are both 2. And for example, here in this slot, there will be the state which corresponds to 0A, 0B, and here the bros 0A, 0B. And according to this labeling, this will be C00. So the lower index is corresponds to the state on the system A, and the upper index corresponds to the state on the system B. So here we have 0, 0, 0, 0. Okay. Then if we fill out this matrix corresponding to this formal expression here, what we get is, so first let me just label which states go where. So here we have 0A, 1B, 1A, 0B, 1A, 1B. And in the columns, correspondingly, we have the same, but with the bras. So we have 0A, 1B, 1A, 0B, and here we have 1A, 1B. So here then we have 0, 0 on A, 0, 1 on B. Here we have 0, 1 on A, 0, 0 on B. Here we have 0, 1 on A, 0, 1 on B. And so on. So for example, in this slot, we'll have 0, 0 on A, 1, 1 on B, and so on. Is it in general clear how we go from this bracket notation to the matrix, to how we fill out the matrix? Yes.
Isn't this always how you choose the order of the basis vectors? So that, for example, I mean, the order you can choose in the way you want, I think.
So this, this way of ordering things, it comes from the definition of a tensor product. So of course you can redefine the tensor product in a different way, but in the classic definition that we have, this is the way we order things. So first the first system always goes first, and then we just go through all the states on the second system, and then we go to the next state on the first system, and so on. Okay, so now let us see what happens if we trace out the system B. So we trace out the second system. So per definition, we just calculate the sum over M of the following. So we just sandwich our density matrix in between the basis states for the second system. And we don't do anything else on the first system. Okay, so then now let us just plug in what we have here. And what we get is sum over M, R1A, M on B, sum over I, J, K, L, C, I, J, K, L, I, J, A, K, L, B, and then we have again identity on A, tensor product, ket M on B. Okay, so we take out all sums. So here we have M, I, J, K, L. Nothing, so then we have our coefficient. Then nothing happens on a system A because we have here the identity and another identity. So we just keep it the way it is. Tensor product. Here we have the state on B, which is sandwiched in between the bra M and the ket M. So what we have here is M, K, L, M. Okay, so because we have chosen the orthonormal basis, this scalar product gives us the Kronecker delta, which is 1 for M equal K and 0 otherwise. And here we get the same Kronecker delta, but delta ML for the indices. This means that the elements of the sum are non-zero only if M equals to K and also M equals to L. So basically, then from this we conclude that the only non-zero elements of the sum are those for which M equals K equals L, which effectively allows us to write this as sum over M I J C M M I J on A. So now we get, assuming that we are working with qubits, we get this 2x2 matrix. And so, which would have the following entries. So have 4 entries. So for the this entry, which would correspond to basically 0, 0, we would have sum over M, C, M, 0, 0. The M goes from 0 to 1. So we would get that this is C0, 0, 0, 0 plus C 0, 0, 1, 1, which basically can be interpreted as like sum of these two terms. So the trace of this small submatrix here. Analogously, here, for example, we get, because it's 0, it's 1. So we get C 0, 1, 0, 0 plus C 0, 1, 1, 1, which is the sum of these two terms. Then here we would get C 1, 0, 0, 0 plus C 1, 0, 1, 1, and which is the sum of these two terms, and C 1, 1, 0, 0 plus C 1, 1, 1, 1, which is the sum of these two terms. This one. So basically, here you can see the rule that you can use when you have the tensor product of, sorry, not the tensor product, when you have a joint state on 2 qubits, and you write it in terms of this matrix, then you can easily see what is the state, what is the reduced state on the first system. So what happens when you trace out the second system by just calculating the traces of these 4 submatrices. So, and the special case of this, taking out the partial trace, which we seen in the lecture and we'll see in the following, is that if we have, for example, the joint state of the system, which has a tensor product of 2 states on individual systems, and we trace out the second system, here we can just directly already write that this is just the rho A. but that is a special case. Okay, but if you have systems of a larger dimension, yeah, first writing the matrix might become very bulky. It's a bulky business. And secondly, if you're not sure about which answer you get by just considering the matrix, you can always write it in bracket notation, which should give you definitely the right answer. Is this more or less clear? Please ask me a question if you have any. Okay, no questions? Partial trace, all clear? Good. Okay, now let us repeat what is a swap procedure and why do we interpret it as cooling of a qubit. So basically, we've seen in the lecture that we can apply a particular unitary to swap the states of two qubits. So first we'll consider real qubits, and then we'll consider virtual qubits. So basically, what we have is these qubits, which we label as S and V. And their states can be written as rho S, PS 00 S plus 1 minus PS 1 1 S. So I already write the state of this qubit in its diagonal form. And so first, basically what I do is if I get a random state, I just diagonalize it. And then each diagonal state I can write in this way because the trace of the density matrix has to sum up to 1. So what it means physically, it means that with probability PS, I find the system to be in the ground state, and which is 0, and 1 minus PS. With this probability, I find the state to be, sorry, the system to be in the excited state. And for V, the state of the V, which we call sigma V, I'll write in a similar manner, just for a different probability. Then what is the swap operation? So the swap operation is, so this is 0S, 1S, 0V, 1V. So the swap operation is the following operation. If in a system S, I go from ground state to the excited state, in a system V, I go from excited to ground. And because we are looking at the unitaries, the reversible operations, we also have to define the reverse. So if in a system S, I go from excited state to ground state, then in the system V, I go from ground state to excited. Okay, so basically what this operation does, it takes 0S, 1V, and maps it to, this is a swap, and maps it to 1S, 0V, and here we have 1S, 0V, maps it to 0S, 1V. Okay, and then for all other states, it doesn't do anything. So 0S, 0V maps to 0S, 0V, and 1S, 1v maps to 1s, 1v. So in the last tutorial, we already saw how to write this unitary in bracket form. So we just write that if we have 0, 1, it maps to 1, 0, plus if we have 1, 0, it maps to 0, 1, plus 0, 0 maps to 0, 0, and 1, 1 maps to 1, 1. Okay. In the matrix form, we can write it as the following. So here again, just converting this bracket notation to the matrix form. Okay, so then we have our initial states, joint states of these two systems, which we label as rho SV. We perform a swap operation, and we get the state rho prime SV, which is equal to U swap rho SV, U swap dagger, okay, so yeah, we can do it in the matrix form. So we just write here the U. Thankfully, U is Hermitian, so U swap dagger is just equal to U swap. We don't have any complex elements in the matrix, so it's fine. What is rho SV in this case? So rho SV is just rho S tensor product sigma V. So you can see that because these both matrices are diagonal, then the resulting matrix, the tensor product will also be diagonal. So only have these diagonal terms, and 0, 0 term, which correspond to a multiplication of these two. So here we get PS, PV. 0, 1 term would correspond to multiplication of these two. So what we get is PS minus 1 PV. Then we have 1, 0, which is multiplication of these two. So it's 1 minus PS PV. And finally, the final 1, 1 corresponds to multiplication of these two. 1 minus PS, 1 minus PV. Okay, so now we just write this matrix here again. PS PV, PS 1 minus PV, PV 1 minus PS, 1 minus PS, 1 minus PV. And everything else is 0. And again, the swap. Okay, so what is going to be the answer of this? What's the resulting matrix? Yes? Yes, exactly. So one can go through this and multiply the matrices, which is also fine. One can already see that each of this like basically the operation that happens would only affect the cross terms 0, 1, and 1, 0, which are with these coefficients. And then basically in the final matrix, we will have these two coefficients swapped. So if this is not entirely clear, I would recommend you to also train maybe once to do this matrix type calculation and once also do it with just using Bryan-Ketz notation. Because both methods I think are useful while calculating these things. Okay, so we have this rho SV prime. And here, let us write it in the bracket notation, just again to ensure that we understand how it's written. And factorize it in a way such we can decompose this new state as the tensor product of two states. Okay. Can someone already tell me how I should factorize this in order to come back to the tensor product of two systems? Any suggestions? Okay, so what kind of state we have here? So for example, we just take out for the first two terms PV 0, 0 on the first system. And then we are left with PS 0, 0 on the second system plus 1 minus PS 1, 1 on the second system plus, and for the last two terms, I just take out 1 minus PV 1, 1 on the first system. And I'm left with exactly the same expression on the second system. Okay. This means I can write this as PV 0, 0 S plus 1 minus PV 1, 1 on S, tensor product. By the way, here it's all tensor product, right? Tensor product with PS 0, 0 on V. Plus 1 minus PS 1, 1 on V. And this is basically just rho S prime, tensor product of sigma V prime. So what happened compared to the states we started with? So rho S turned to rho S prime and sigma v turned to sigma v prime, which effectively just swap their coefficients. So they're swapped their PS and PV. And the way we can interpret it is the following. So we know that for each qubit, we can introduce, depending on its state, we can introduce that its temperature. So we can always write that this rho S is a thermal state for some temperature T1. And this sigma V is some thermal state at a temperature T2. And let's say that the temperature T2 is less than the temperature T1. And what we arrive to is that now the first system is a temperature T2, and the second system is at a temperature T1. And that's what we did. If T2 is less than T1, we effectively cooled the first system. So that is the meaning of this operation that we're going to use. Okay. Is this clear? Okay, very good. I see nodding heads. Now, let us proceed to the case when we are swapping not with a real qubit, but with a virtual one. So I was already hinting at this fact while labeling the second real qubit as V. But now we will use a virtual one instead. So what is the main difference of the virtual qubit compared to the real qubit? So in a real qubit, we know when we use real qubit for cooling, we swap our first qubit with the whole system of the second qubit, and that's how we cool. And using virtual qubit, we basically take a particular subspace of a system, of another second system, and we perform a swap operation with that particular subspace. In practice, this means that when we will write the state of the second system, the density matrix of the second system, the state on the subspace would not be a kind of a valid density matrix as in the sums of the populations on these two states that we're going to use in for the virtual qubit is not going to sum up to 1 generally, because there might be some population also on the other levels of this second system. But that is basically one thing that we have to be aware of. So now, so let me see. So virtual qubit swap. So again, we have our system S, 0S, 1S. And then we have system, I don't know, we can call it E or whatever, out of which we kind of take this virtual qubits we're swapping with. And say that we take the virtual qubit that we consider is between two levels of the system, which I call I and J. And so I forget about all other states in this more complicated system, and I only use these two states. Then I write the state of the system. Actually, let me still call it V. It's easier. Sigma V as some state on this, on the rest of the levels, plus this particular populations on the levels of I and J. So it's going to be population PI on level I, plus population Pj on level J, plus the rest of this matrix, which I label as sigma v. So this is the sigma v tilde. So this is the difference with how we wrote the state of the qubit v before. We have this additional term, and for these two terms, which can be interpreted as like 0 state of the virtual qubit and 1 state of the virtual qubit, the coefficients in front of them do not sum up to 1 necessarily. Okay, and then there is a norm of the state, and V we code, which is the sum of these two populations, Pi and J. Sorry. Then the swap procedure that we do is the same as we've done before. So 0, if the qubit is in a ground state, and going to the excited state, then here we have the opposite. And if it's going from the excited state to the ground state, then here it goes like this in the other direction. So this transformation can be written as 0 SJV maps to 1 SIV and 1 SIV maps to 0 SJV. Okay. So now we basically repeat our operations that we did. So maybe I can even use what I already wrote here. Maybe not. Let me. Erase this. So we again write our transformation. This time it's easier to just write the transformation in terms of bras and kets. And to see the transformation, we just write the initial state on both systems, rho SV, which is rho S tensor product sigma V. Okay. And we would have here PS00 plus 1 minus PS11. This is on the system S. Tensor product with the state sigma V, which is PI II plus PJ JJ plus some additional state on or in the rest of the Hilbert space of the qubit B. Okay, so what we get here is PS of PI 0I 0I plus so maybe a small comment, I should have done it before. So when we write in this bracket notation for 2 systems or more systems, like we don't always write 0, 0, tensor product II, and so on. So we, for simplicity, we just write it as a more states, more labels in one ket and a bra. So the first label is always the first system, then the second label is the second system, and so on. And the same goes for the bra. So basically what this notation means is that 0, 0 on the first system, tensor product II on the second system. just a comment to make sure that we're all on the same page on this. Okay, let us continue. So here we have PS, PI, 0J, 0J, plus 1 minus PS, PI, 1I, 1I, plus 1 minus PS, PJ, J by the way, 1J, 1J. Plus, we still have the term. So for the sake of writing the multiplication with this term, I just write it as rho S. So this is rho S. Tensor product sigma V tilde. Okay, so what happens after we perform this swap transformation? So the swap transformation only like in case of the qubit V, it only affects what happens in the subspace of the states I and J. So according to this transformation, like nothing happens here because here we don't have the states I and J. This state 0I is mapped to 0I, 0J is mapped to 1I, and here as well. And 1I is mapped to 0J. And 1J is just mapped to 1J, so nothing changes here. So what we arrive to is just the case when we have these two coefficients swapped. So we have PS, PI, 0I, 0I, plus PS, PI, 1I, 1I, plus 1 minus PS, PI, 0J, 0J, plus 1 minus PS, PJ, 1J, 1J, plus rho S tensor product sigma V tilde. And here, in the same way that we did for the swap with the real qubit, we can factorize these four terms in a way that we can get more meaningful expression. So let me. Sorry. So thank you. It's going to be rho SV prime. So so basically what we do, we have rho SV, then we apply the swap, and we get rho SV prime. Any questions as to what happens with the swap transformation there? Do you see how we applied the swap transformation just using the brackets description of the state? Yeah, okay. I'm happy to see nodding heads. Okay, so I need to see that state myself. And of course, I'm sorry for the confusion. Well, like I'm confusing myself. This is J. This is also J. I'm sorry if I write I and J very similar. Okay. So now we just massage that state. Or even, let's do it this way. So since Ralph already told you about like repeating and using another copy of a virtual qubit or a real qubit, the way we usually proceed with the cooling is we just use one virtual qubit, we perform the swap operation, we throw out that virtual qubit, we take another copy of it, and we repeat again. So for that reason, I'll just already kind of think about that I will need to eventually throw out this virtual qubit, and I'll just compute the reduced state on the system S that we would have. So I'll just trace out the second system. So for the first, since all terms, the first four terms are all diagonal with respect to the second system, the first system as well, then I can just easily trace out the second system. And what I would get is PS, PI, 0, 0, S plus PS, PJ, 1, 1 on S plus 1 minus PS, PI, 0, 0 plus 1 minus PS, PJ, 1, 1. And yes, plus when I trace out the second system out of this tensor product, I just get our initial state rho s. I think I need to make a break here. So the next step that I will do is maybe let me just finish writing this. So here I know that PI plus PJ, we labeled it as this norm NV of the state. And so here what I can do is I can rewrite this as NV PI yes, PI plus PJ 0, 0 plus PJ, PI plus PJ 1, 1 plus 1 minus NV PS 0, 0 plus 1 minus PS 1, 1. So if you want, in the break, you can convince yourself that this is correct. And then I can write this as NV, the thermal state on system S, but of the temperature, virtual temperature, which corresponds to the temperature of the virtual qubit. And 1 minus NV rho s. So basically, what the swap operation has achieved on our qubit is that with probability NV, it would turn it into the state of the temperature, of the virtual temperature of the qubit, and with probability 1 minus NV, the state will stay the same. And in the following, we'll see what happens when you repeat this procedure n times, and why does it lead to further and further cooling of the system. Okay, you can have a 5-minute break. And we'll restart at 10 to 1. Yes.
Just in the sense, with the probability NV, our system will change the temperature, and with probability 1 minus b would stay the same.
Yes, exactly. Yeah, that's the physical interpretation. Yeah.
Thanks.
Yeah. Cool.
Swappen är ju den här på det ligger på
Yes.
I have a question with the
Yeah.
start. So when you take the generic qubit,
Yeah.
I know we can always diagonalize it.
Yeah.
But then it's not that it's plenty eigenbasis anymore, is it? Like when we take it, it's eigenbasis where it's diagonal, or is it possible to have it always diagonally in a eigenbasis?
Yes. Wait. So.
So for me, it looks like we always take a qubit that's diagonal in the energy eigenbasis. The question is it always possible, or is it an assumption that we, like, is it possible for a generic qubit?
Yeah. Okay. It's an assumption that we write it in its own eigenbasis, and then the Hamiltonian would be also diagonal in the same basis.
Okay.
But I mean, yeah. But that's kind of the that's the assumption that rho commutes with h, basically.
Okay. Okay. Thank you.
Okay, let's continue. So basically what we've just seen here is that now one swap operation with the virtual qubit maps the initial state rho s to the state rho s prime, as we called it, which is NV tau s beta v plus 1 minus NV rho s. Okay, so actually looking at this formula, you can see that this is a more general case. So in the beginning, we just looked at the swap operation with one real qubit. And for one real qubit, this NV, the weight is 1, because the sum of the populations on the ground and excited level is 1. So basically, what we would get in that special case is that rho s prime is just the thermal state of the temperature of that qubit, of the second qubit we're swapping it with. But we see that here when we swap it with the, not the actual qubit, but the virtual qubit, there is some probability that the system will stay in its initial state. So then to ensure that we cool the system more and more, we need to apply this operation many times. And to see how we can do it, so let us how we can write out the result of such application. We can rewrite this state as tau s of beta v plus 1 minus NV rho s minus tau s of beta v. Okay, so Now, what happens if we apply the operation the second time? So let's say we map it to rho s 2 primes. So this operation, what it does, as I said, it's with probability NV maps it to the thermal state with the temperature of the virtual qubit, or with probability 1 minus NV, it just stays the same. But now the same means it's rho s prime. So here what I would get is NV tau s plus 1 minus NV tau s plus 1 minus NV rho s minus tau s. Okay. If I open this up, so here I would get NV tau s plus 1 minus NV tau s, which will give me tau s. Sorry? This one. No, it's NV tau s, because you see that the operation, what it does physically, it with probability NV, it maps it to the thermal state, and 1 minus NV, it stays the same. So here I do the same, but I apply it to the rho s prime, which is this state, which means that it's still mapped to tau s with probability NV, and 1 minus NV, it is rho s prime. So, but here, summing up these two terms, I get tau s, and then in the rest, I get 1 minus NV squared rho s minus tau s. And by induction, one can show that after applying the operation n times, we would get rho s n, let's label it like this, which would be tau s of this beta v plus 1 minus NV to the power n rho s minus tau s. Actually, let me use the smaller n to avoid confusion with the norm. So we see that as n grows larger and larger, this term becomes more and more negligible. So then we can say that the state of this qubit S comes closer and closer to the state with the virtual temperature of the virtual qubit we are swapping it with. Okay. So what you will need to do, if this is all clear, hope it is, please ask me anything if anything is unclear. Okay. So in the exercise, so the first exercise just concerns swapping the qubit, which is in a fully mixed state initially, with the virtual qubit, and then looking at how many times it needs to be swapped to reach another state and so on. For a particular example of the initial state of the qubit and particular example of the virtual temperature of the virtual qubit we're swapping it with. And also you'll need to calculate the energy change for one step of the process, which I believe Rolf already did in the lecture, but it's good to repeat. And in the second exercise, you'll need to apply absolutely the same procedure, but for a more like hands-on example, when we have our qubit and we want to cool it using a qutrit. So a system which has 3 basis states. And then you will need to see how we can use, say, like 2 virtual qubits of this qutrit, which will be this one and this one. And using them, what is the optimal procedure of cooling the initial qubit? So should I take one qubit and then the other? Should I only use one qubit, the first one or the second one, and how I need to combine them basically. Okay. So now we are done with the cooling for today, and now we go to the final topic. Yes.
What is the interpretation that the system is closer and closer to the temperature of the virtual source?
So it's basically the same as the interpretation of when we swap it with a real qubit. So say it starts in a state with the temperature higher than the virtual temperature of the virtual qubit, and then we want to cool it, and with each application of the swap operation, the temperature of the qubit is less and less, and it grows, and it like diminishes closer to the virtual temperature of the virtual qubit.
Okay. So they kind of become equidistant.
They kind of become of the same temperature. Yeah. Yeah. Okay, so now we come to the last topic, which is composing virtual qubits. And in the lecture, you've seen how to compose 2 virtual qubits. Now we'll compose 3 virtual qubits. And also we will see how to understand and extend this notion for an arbitrary number of virtual qubits. So we start with 3 systems, which can be of arbitrary large dimension. And we just choose a virtual qubit in each one of them. So, wait, where's my marker? Okay. It's black. So system A, yeah, some levels. System B, also some levels. System C, also number of levels. So now we choose 3 virtual qubits. So say first we choose here, we choose this one with the energy difference delta EA, and this will be E I A E G A. So it's just 2 levels, which are levels I and J of this system A. Then we choose 2 levels of the system B. For simplicity here, I will also call them I and J, just to not use too many letters. Here, the energies will be different, obviously, because it's another system. And then the difference would be delta EB. Here I do the same. Say I choose these 2 levels. The energy difference will be delta EC. And again, I just label them as I and J for convenience. It's going to be I, J. So this is on system C. This is system B. This is system A. And I have these three virtual qubits. And now I want to know how to combine them and which new virtual qubits I can construct by combining these three. Just as a reminder, what we did for 2 qubits, and also for you to see the pattern of what we're doing for 2 qubits. So now let us forget that the qubit C is here. Let us just consider this two. What are the basis states and the energy eigenstates of these 2 virtual qubits? So it's going to be actually, let me do the following. So again, a notation, just a slight notation change. Whenever I would say I would mean 0, and J, I would mean 1. This is just also easier for the labeling the states and seeing what is the mathematical pattern for finding the new virtual qubits. So for 2 qubits, my basis states would be 0, 0 on AB, 0, 1 on AB, 1, 0 on AB, 1, 1 on AB. And here, the energy of this state would be EA0 plus EB0. Here would be EA0 plus E1B. E1A plus E0B. E1A plus E1B. So let us consider each pair of the states and see if we can construct a virtual qubit out of it. So a new virtual qubit. So if I say, take the states 0, 0 and 0, 1, I can actually factor this as just the state 0 on the first system and 0 and 1 on the second system. Which means that if I look at the virtual qubit which consists of these 2 states, then I can see it as just like state 0 on the system A and the virtual qubit on the system B. With the same virtual temperature as the virtual qubit on the system B has. So this is not a new construction. So the same goes for when we consider state 0, 0 and 1, 0. Here I can factor out the second system and see it as a virtual qubit on the first system and just 0 state on the second. Also not new. What is new is if I take 0, 0 and 1, 1. Here I cannot factor out anything, and this would comprise a new qubit with a different virtual temperature. Then 0, 1 and 1, 0 also is a new qubit. And so then, for example, 0, 1 and 1, 1 is not 0, 0. Sorry, 1, 0 and 1, 1 also not. So basically, we have these 2 new qubits. So can somebody tell me, so if I take a particular joint state of these 2 qubits, with how many states I can pair it with, so I get a new virtual qubit? So here, for example, if I take state 0, 0, the one, I can only pair it with one other state to create a new virtual qubit. What is the rule? Do you see any pattern here? How we construct the states? Different values on the same positions, exactly. Yes, very good. So basically the idea is that whenever we can factor out one system for both of these states, so for example, here 0, 0, and 0, 1, we can factor out 0 for the first system, we will not get a new virtual qubit. We'll get some old one, which we already considered. To not be able to tensor something out, we need to pair the state with a state which would have opposite entries at each place for each system. So here we have 0, 0. It can be paired with 1, 1. So basically, we just negate that binary sequence of 0, 0, and we get 1, 1. And here it's the same. We negate the 0, 1, we get 1, 0. That's why I went for labeling it as ones and zeros, because here you can see kind of the procedure that we take the sequence of zeros and ones, we negate it. This is the second state, and pairing these two states, we get a new virtual qubit. Okay. Now let us apply this logic for 3 qubits. So having this algorithm, you should be able to tell me after I write out all the basis states for the 3 virtual qubits composition, which of these states give you new virtual qubits. So for 3 qubits, I have the following states. So 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. I will not write now the same energy eigenbases that I wrote there. I'm sure you can do it on your own. Now, please tell me with which state I can pair 0, 0, 0 to get a new virtual qubit. Yes, exactly. So we compare it with 1, 1, 1.
Excuse me, I think your microphone. No, your microphone.
My microphone is off. Okay, now is it?
Yes.
Okay. Fine. So now basically the second state, which state are we pairing it with? Yes, exactly. Third state? Yeah. And the fourth state finally? Yes. So see that we have this 4 new virtual qubits. Okay, more general question. If I pair n virtual qubits, how many new virtual qubits can I kind of squeeze out of that?
Just those 4.
No. Yes. No.
No.
So here we can squeeze out. So we have 8 basis states, right? 2 to the power 3. And for each state, we can find a pair. So there is only one pair for each state, which means that the total number is 2 to the power 3 over 2, which is 4. For n virtual qubits, the total number of basis states is 2 to the power n. And then it's over 2 to the power n minus 1. Sorry, was that your answer? Sorry, I somehow understood 2 to the power n minus 1. Sorry, you're correct. Now I realized it. Yeah, so the idea here is that for each state, there is only one negation of this binary sequence. So for each state, there is one pair. So in total, it's half. Okay. Yes, exactly. Yeah, that's a good comment. So, yeah, having already considered all the virtual temperatures for n minus 1 qubits, how many new virtual temperatures adding one more gets us? Yes. Which thing? Yeah, okay, that was really good. Okay, so now let us just, for training, derive one of the virtual temperatures for the 3 qubits. So for example, between the first pair, 0, 0, 0, and 1, 1, 1. So for this, we'll also need the populations on different levels. So first, what is the having these 3 qubits? Let us consider the virtual temperature between these 2 states. What is the energy difference between these 2 states? This is easy. This is just delta EA plus delta EB plus delta EC. So here we can even just draw it as label as delta E. This is 0, 0, 0. This is 1, 1, 1. Here it's delta E. Okay. And now let us also, maybe there I'll write the populations on different levels and the virtual temperatures for each of these virtual qubits. So here I can write that the virtual temperature of this qubit, which I label as beta VA, we have delta EA equals P, say JA, okay. Yeah, PJA over PIA. So I label the, actually since I 0 and 1s, let's just do it 0 and 1s. So here I would have the population P0 A, and here P1A. And here the same, P0B, P1B, and here P0C and P1C. Then this is the virtual temperature of the first virtual qubit. Then e to the power minus beta VB delta EB equals P1B over P0B. This characterizes the virtual temperature of the second qubit, and the same for the third qubit. Okay. So now we need to write the virtual temperature for this qubit. for this, we need to know the population of these two levels. If the population of the level 0 here is P0A, population of level 0 for B is P0B, population of level 0 for C is P0C, then the population of this level 0, 0, 0 is just multiplying these three. This you will also see if you just write the composition of these three qubits as the tensor product of the states on the corresponding systems, and then just look at the part which is relevant for the 0 and 1 states on each qubit, on each system. And similarly, the population of the second level, which is 1, 1, 1, is P1A by P1B by P1C. Okay. Given this, we can write our Gibbs ratio, which will capture the virtual temperature of the system. So E to the power minus beta V delta E will be equal to the population on the excited level divided by the population on the ground level. Okay, how can I express that in terms of the virtual temperature of each qubit? I know that this ratio is E to the power minus beta A delta A. This ratio is the same thing for B, and this ratio is the same thing for C. So I can just write this as E to the power minus beta VA delta EA, E to the power minus beta VB delta EB, E to the power minus beta VC delta EC. On the other hand, I know what delta E is. So delta E is the sum of these three. So I can write this as minus beta V delta EA plus delta EB plus delta EC. Okay, I have two exponents. I can, since they're equal, I can equate their arguments. So what I get is beta V delta EA plus delta EB plus delta EC equals the sum okay, and from this I conclude that beta V is equal to, I think the marker is losing its life. So change, so it's going to be beta VA delta EA plus beta VB delta EB plus beta VC delta EC over the sum of the energies. Okay, so that's how we, in general, find the virtual temperature of this new, one of these new virtual qubits. And the same procedure can be done for the remaining three pairs of the states, which you will need to do in the exercise sheet. Okay, I think this is all I wanted to say for today. Please ask me questions if there are any.